Luke Stein here, and in this short video, I'm going to introduce a basic set of quantitative tools for analyzing the time value of money. So the time value of money, or TVM, is going to recognize that generally investors would like to have more money, but they'd also like to get paid sooner. It'd be nice to get both. It'd be nice to have a lot today, but it can be hard to achieve both of those goals. And so typically, investors or financial analysts more generally are going to face trade-offs between having less money today and having more money in the future. The quantitative tool that we use for evaluating those trade-offs are called TVM, or time value of money analysis tools. So let's start thinking about the time value of money by analyzing a simple compound interest over time problem. Suppose, for example, that you deposited $500 into a bank account, and that bank account earns 6% interest every year. How much are you going to have in your account at the end of 1 year? Well, of course, you're going to have back the $500 that you started the year with, and we call that amount principal, but you're also going to have earned 1 year of interest. And how much interest will you have earned? Well, the 6% interest that you earn on your $500 principal is going to be 6% of $500, or $30. So you're going to wind up at the end of the year with $530. Excuse my handwriting, please. So let's make that calculation a little bit clearer, someplace you can see it better than you can in my handwriting, which is in Excel. If you think about starting the year with $500, after 1 year, you're not only going to have back your $500, but you're also going to have 6% interest times the $500 of principal that you started with. You're going to end the year after 1 year with $530, having started the year with $500. So what about after 2 years? Well, of course, after 2 years, you're going to have not only your $500 principal, okay, plus you're going to have the $30 of interest that you earned in the first year. You're going to earn another year's worth of interest, or another $30, what we sometimes call simple interest. That's not the end of the story, though, because you're also going to be earning interest in the second year on that interest that you earned in the first year. So how much is that going to be? Well, you're going to earn 6% interest in the second year on the $30 of interest that you earned in the first year, or another $1.80, adding up to a total of $561.80. Okay, so how can we think about the calculation that we just did in a slightly more formal way? We can type that up in Excel, and we can note that in year 2, you not only are going to earn 6% on the principal that you started with, or $500, but you're also going to be earning 6% on the full $530 that you ended year 1 with. So we are going to say at the end of year 2, you'll not only have the $530 that you started year 2 with, but you're also going to have 6% interest on that full $530 for a total of $561.80. So we can do a tiny bit of algebra and just rewrite that a little bit more simply, and note that if in each year we end the year with what we started with, that's 1 times the previous year's balance, plus the interest that we earn on the full balance we started the year with, that's going to be the interest rate times the previous year's balance. We can write this as the previous year's balance, or in year 2, $530, times 1 plus the interest rate of, in this case, 6%. And so multiplying the previous year's balance times 1 plus the interest rate, we get the end of year balance in the following year. Okay, so after 1 year, we've got $530. After 2 years, we've got $561.80, which represents principal of $500, interest earned in the first year of $30, simple interest earned in the second year of $30, and compound interest earned in the third year of $180. We can just continue thinking about running the same calculation in year 3. We're going to start the year with $561.80, which we can multiply by 1, because we're going to still have that at the end of the year. Plus, we're also going to multiply it by 6%, the interest that we earn, not only on our principal, but on all of the interest that we've earned to date. We're going to end year 3 with a balance of $595.51. And I've written that formula in such a way that since each of these refer to the cell above, I should just be able to either copy and paste that formula or in Excel, grab the handle and drag it down. In this case, to get year 4 and year 5 balances by the end of year 5, I'm going to wind up with $669.11. Okay, so what have we done? We've basically said that after n years, after some number of years, we're going to take the principal balance that we started with, okay, at the beginning, which in this case was $500, and each year we're going to multiply it by 1 plus, let's call it the interest rate R. So after 1 year, we're going to have $500 times 1 plus R, or 1.06. After 2 years, we're going to have it multiplied by 1.06 times 1.06, and we're going to keep doing that until we've multiplied it a total of n times. And what's another way of saying that same thing? We're going to take our original principal value and we're going to multiply it by 1 plus R multiplied to the n power. So in the last example that we looked at, that would look like $500 times 1.06 to the 5th power, because we've invested our $500 and earned a 6% rate of return for each of 5 years. And more generally, we could write this not as using a generic $500, but instead using what we're going to call the present value, or the PV of the investment, okay? And we're going to get a general formula which says that the present value multiplied by 1 plus the rate of return raised to the nth power is equal to what we call the future value. Okay, so this is going to be our basic time value of money formula. The present value times 1 plus the rate of return raised to the nth power equals the future value. We can check that that actually works in Excel. And so we could go directly to the answer by saying that after 5 years, we're going to have $500 of principal, or present value, multiplied by 1 plus the 6% interest rate. And in Excel, we're going to use a caret, or shift 6, to get that exponent. And after 5 years, the balance in our account is going to be $669.11. So we can just go straight to the answer. So a general principle for solving basic time value of money problems is going to be to start with a timeline, think about what cash flows are going to happen when, we're going to identify which numbers we know, and then figure out which unknown numbers we're trying to find. So let me take the problem that we just analyzed, and let me show you how I would think about it in this framework. If we draw our timeline, we're imagining investing $500 in a bank account, or saving $500 in a bank account, and I'm going to draw that as a downward pointing arrow on my timeline. Why downward pointing? Because the general norm in drawing these kinds of cash flow diagrams is that whenever we think about money coming out of my wallet or my account, out of my pocket, I'm going to write a downward pointing arrow that's a negative cash flow. So I'm going to take $600 out of my wallet and I'm going to go put it in the bank. That's a negative $500 cash flow. And then time is going to pass and I'm going to receive some unknown, in this case, future value, or FV, at some point in the future. And when is that point in the future coming? Well, it could be in the 3 problems we just analyzed: after 1 year, after 2 years, or after 5 years. Now note, in the simple problem we just solved, these are the only 2 cash flows that happen. There's a present value that happens today, and in this case, it's a negative cash flow, and then a future value, which happens in the future. When I make a withdrawal, I'm going to receive that money into my wallet, so we get a positive cash flow. More generally, we're going to think about time value of money problems where we also allow the possibility of some additional cash flows on the timeline. So in particular, we're going to think about there being a present value, a cash flow that happens at the beginning, a future value, a cash flow that happens at the end. But we're also going to allow the possibility that every period along the way, the investor either makes or receives some additional payment. Maybe that's additional savings that you're putting into your bank account. So, every year I take an extra $100 and save it, add it to the bank account. That would be another negative cash flow happening at each of these points of time. And so we would be adding additional negative cash flows, PMT, at each point in time. Alternately, it could be that maybe I'm making withdrawals at each point of time. And so maybe I make a big initial savings and then I'm going to draw down that balance year by year, in which case there would be positive payments received. So what are the additional quantities that we need to know in order to complete this analysis? We need to know not only the PV and the FV, we need to know the payments that happen at each point of time, where in the problems we solved before, that payment was 0. There were no additional deposits or withdrawals. over each of the, let's say 5 years, the money stayed in the account. And then we need two additional things. We need to know the rate at which this investment is either earning a return or in which I'm paying interest on the investment. And we need to know the number of periods, or NPER. So generally speaking, our formula for solving a TVM problem, or kind of our recipe, is going to be first figure out which of these 5 things, PV, PMT, FV, rate, and NPER, which of them we know, and hopefully we're going to be able to figure out that we know or have enough information to get 4 of those 5 things. And then if we know 4 of them, there should be 1 left. That's the unknown that we're trying to find. So that's going to be kind of our formula. So what do? It turns out that unlike the simple FV and PV where payments were 0 that I just showed you, there's more complicated formulas once we introduce the payments, and you don't need to know what those formulas are. Why not? Because Excel has all of these built in, and the name of the function in Excel is just based on the thing that you are trying to figure out. If you're trying to figure out the number of periods, you're going to use a function called NPER for number of periods. If you're trying to figure out the rate of return, you're going to use a function called rate. If you're trying to figure out the PV, that function is going to be called PV for present value. If you're trying to figure out the payment every period, that's going to be PMT. And if you're trying to figure out the future value of the investment, that's going to use an Excel function called FV for final deposit. And we're always going to, in class, be able to use Excel. In your life as a financial analyst, you're likely to generally be able to solve all these problems in Excel. But I would note that you can also go old school. And if you have a financial calculator, right up at the top, I don't think we're going to get focused, but there's generally on any financial calculator going to be buttons that say exactly these 5 things: NI, PV, PMT, and FV. So let's start by taking the problem that we just solved in Excel, and let's think about trying to take that and use those built-in functions that we mentioned in Excel. So we've solved this one manually, but the function that we're looking for is going to be which one? Think about it for a moment. Which of these 4 things do we know, and which are we trying to figure out? Well, we know the number of periods. We know in the most complicated version of the problem that we solved that we were going to leave our money in the bank for 5 years. We know the rate. We know that each period our investment was going to earn an investment of 6%. We know that the present value was $500, the principal that I initially invested. But once I put this in Excel, I'm going to call that a negative $500 because it's a deposit. The payment made every period is 0 because I made no additional payments every period. And so I'm going to use a function called FV in order to figure out what that final deposit withdrawal or repayment was. So the Excel function I'm looking for is called PV. And the PV function, I know it's a little bit small, but Excel gives us some tips. It says, first, give me the rate. What was the rate? The rate was 6%. Second, it says, give me the number of periods. The number of periods was 5 years. Next, give me the payment that happens every period. There's a $0 deposit or withdrawal every period. Then it says, give me the FV. Sorry, I'm using the wrong function. We're supposed to be using the FV function, the future value function. And I figured that out because it was asking me to type in the FV before, and I was like, FV is exactly the thing I'm trying to figure out. So I should be using the FV function. First, it wants the rate. That's going to be 6%. Then it wants the number of periods. That's going to be 5 years. Then it wants the payment every period. That's going to be 0. Then it wants the present value, which is going to be minus $500. There's an additional optional argument called type that I'm going to leave for now blank. And what do we get? We get $669.11. Boom, Excel solves this for us immediately. So let's try some other examples. Example 1, suppose you have $3,000 today and the bank is paying 4% per year. How much will you have in your account in 7 years? Note, this is exactly the same problem that we solved before, except with different numbers. So we actually should be able, if we needed to maybe even pencil and paper this one, just using exponentiation, the present value times 1.04 to the 7th power. But we don't need to because Excel or our financial calculator can do the job for us. Do we know the number of periods? Yes, we do. This is 7 years between today and when we're going to make our withdrawal or check our balance. Do we know the rate? Yes, we know the rate is 4% per year. Do we know the present value of the investment? Yes, we know that there's a $3,000 deposit. And because it's a deposit, we'll call that a negative number. Are there deposits or withdrawals happening every one of those 7 years? No. So we're going to make the payment 0. Do we know the future value? No, that's the thing we're trying to figure out. So let's go to Excel and type this thing in. Can I get both Excel and the slide on at the same time? No, I don't think I can. That's a new example. Let's just switch on over to Excel. So now we're in example 1. We're going to use the FV function again. The rate at which we've invested is 4% per year. The number of periods that we've invested for is 7 years. The next thing we need is the payment per period, which in this case is 0. We're going to put in the present value, which is that minus $3,000 that we've deposited today. Once again, we're going to leave that optional type argument out at the end. And so Excel tells us that we're going to end the year with $3,947.80. Okay, let's get that number on here. 3,947.80. Let's round it to 3,948, $3,948 approximately. Okay, next problem. Suppose that you raise $30,000 today from investors to start your new business, and those investors expect to earn 4% per year. How much is their investment going to have to be worth 7 years from now in order to meet their demands? So if we think about trying to draw that timeline again, how's the timeline going to look? Well, from your perspective, you're going to receive $30K today, and you're going to have to make some payout to investors, maybe after doing an IPO, paying a dividend, selling the business, and that's going to have to be big enough out of your pocket in order to earn them that 4% return over the course of 7 years. So note, actually, the shape of this timeline looks exactly the same as the one that we drew before. What's the difference going to be? Well, it's just that before the timeline looked like this. I'm going to back up so you can see my arms pointing like the arrows. Boom. Okay. And now we're just flipping the arrows on their head. Okay, so this is actually often the case. If you have a negative PV, you're going to wind up with a positive FV. That's like making a deposit in the bank and then a withdrawal later. If you have a positive PV, you're going to have a negative FV. That's like receiving a loan or an investment today and needing to pay it back sometime in the future. So what exactly are the numbers? Well, we know that investors are going to be waiting for how long? They're going to be waiting for 7 years. They're expecting to earn a 4% annual rate of return. You as a founder are going to have a positive 30K cash flow today. Of course, from the investor's perspective, that's a negative 30K cash flow. There's no additional funds getting raised from these investors every year in between. And so we're going to have to figure out what that future value is. And in fact, if you're paying close attention, you'll note that in fact, this is literally the same question as the one we just answered, except the amount of dollars is multiplied by 10. And the sign is changed. So this is a 4% rate, 7 periods, 0 payments along the way, and a present value of positive 30K. You should expect to pay out $39,478, or call it $39,500 to investors 7 years from now. Okay, example 2. These kinds of problems are called discounting problems. What are discounting problems? Discounting means that you are trying to find the present value. Note, in example 1, we knew the present value. We were trying to figure out the future value. Now we're going to do exactly the opposite. Suppose that you know you're going to need $1 million in order to retire 20 years from now, and you expect your investments to be able to grow at 5% per year. How much do you need to have today if you're going to make no more deposits into your account? So we read the sentence, and ignoring the title of the slide, suppose you didn't know that, we're going to figure out what do we know and what are we trying to figure out? Well, my cash flow diagram says deposit today. That's going to be a negative present value. How much am I going to deposit today? I don't know. That's the thing I have to figure out. But I know that I'm going to wait 20 years. I expect to earn a 5% rate of return each year. The prompt says there's going to be no more deposits made into the account, so a 0 payment every year. And in the future, I'm expecting to have a positive $1 million balance that I can take out of the account, receive in my pocket. So I should expect to have some kind of negative PV today. How big is that negative PV going to be? Well, if I want to find a PV or a present value, I told you those problems are called discounting problems. We're going to use the PV function, and I'm going to put in the 5% rate that I expect to earn. I'm going to put in 20 for the number of periods. The payment every period along the way is going to be 0. I've got a $1 million face value at the end, or future value rather. That's 1, 2, 3, 4, 5, 6. Okay. And I need to have $377,889 today, rounded to the nearest dollar. Okay. That should be enough to get me that $1 million in retirement. A couple more examples. I will distribute these slides, which will talk about how you could do this using algebra, although we did it in Excel. Suppose that we had $120,000 already saved in order to send my kid to college, and I expect to send her to school in 4 years because she's a high school freshman now. Suppose I expect I'm going to need 240 grand in order to pay her tuition. And suppose that I just am going to write that check as soon as she enrolls. So 4 years from now, suppose that I expect somehow to earn 12% per year on my investments, realistic for a risk-free investment. If there's no risk in any of this, risk is coming later. How long? I already presupposed the answer to the question, which maybe wasn't right. How long is it going to be until I can send her to school? So suppose I have 120K and I need to double that. I can earn 12% per year, and I want to know how long it's going to take me. Can she go to college in 4 years? We'll see. So this question is asking me to find the number of periods before she can go to school. So that's our unknown quantity. I can earn a rate of 12% per year. I'm going to make no additional savings or deposits along the way, and I expect to receive 240K at some point in the future that I'm then, of course, going to have to pay in tuition. So how much am I going to deposit today? Well, I'm going to go send $120,000 off into the stock market right now in order to try to double that. So the sign flips between the negative cash flow today. I've got to send that money off to my investment account and a positive future value cash flow in the future. So using Excel, what function do I need? Well, I know all these things, except I don't know the number of periods. And so I'm going to use an NPER function. The name of the function is always the thing I'm trying to calculate. I'm going to try to calculate the number of periods it's going to take at a 12% rate. Next up, it wants the payments, no deposits along the way, to turn a negative $120,000 cash flow into a positive $240,000 future value. Okay. And the answer is it's going to take a little over 6 years, 6.1 years. So she's going to need a little bit of time after graduating if she's a freshman now before she's ready to go off to school, or I got to find a cheaper school, or I have to invest more than 120K now, or I need to earn higher than 12% rate of annual return. Note, by the way, if I kind of screw up the signs on my cash flows, so if I do something like I said, sure, let's calculate the number of periods at a 12% rate of return with a zero payment to turn $120,000 into $240,000, I'm going to get an error. And why am I getting that error? It's because I didn't get the sign right. I put in a positive 120K and a positive 240K. And Excel's like, Luke, you're not going to be able to do that. What would that represent? It would represent some kind of investment account where I started out by withdrawing $120,000 from the bank or my investments. And then 6 years or some number of years in the future, I withdrew another 240K. So you can't withdraw what you don't put in. You can't have a positive future value with a positive present value, unless, of course, you have some negative payments that you make along the way. So we are going to have to be careful about signs, although often if we've made a sign error, Excel or our calculator are just going to tell us by giving us an error. Okay, next example problem. Let's get it going. Let's try, there are slides describing how to do this that I made doing this with algebra, which would involve taking fractional exponents, but we won't. Okay, suppose that we do have payments along the way. In this case, this example is going to ask us to find a future value with payments along the way. So suppose that you just had a son and you want to set aside $5,000 a year for each of the next 18 years. You think you can earn 6% annual returns. How much are you going to have at the end of the 18 years? So again, we're going to start by thinking, what do we know? What do we need to figure out? Do we know the number of periods? Yes, we know that we're going to be making investments for each of the next 18 years. Do we know the rate of return that we're going to be able to earn? Yes, we assume a 6% annual rate of return earned. What about the present value? Well, the present value is the amount of money that I start with at the beginning. How much do I have now? Well, it looks like I'm starting out with $0, but I'm planning to make deposits or savings of $5,000 per year for each of the next 18 years. So what's the sign on that? Since I'm sending the money off into the market, I'm going to call that a negative $5,000 payment every year. And then I'm going to ask the question, what is the future value of this investment? So how does this thing look? It's going to look like this. It's going to look like a $5,000 investment every year. Okay. And these arrows should be equally spaced and equally sized. Okay. So there's going to be 18 of them. One per year. Let's put in some dots because I didn't actually draw 18. And then at the end of the 18 years, I'm going to ask, what's the big future value that I can withdraw? Okay, so Excel is going to let me solve that problem after I set it up. The function that I need, it's going to still be that same FV function. The name of the function is always the thing I'm trying to figure out. Let's put that up in the middle there. I'm going to solve using the FV function because I'm trying to figure out a future value, the thing I don't know. What's the rate I can earn? It's 6% per year. Okay, next up, it wants the number of periods. I'm planning to save for the next 18 years. What's the payment I'm going to make? Well, I'm expecting to set aside $5,000, so a negative $5,000 per year cash flow. What's the present value that I start with at the beginning? I'm going to start with 0. And once again, I'm going to ignore that type argument at the end. It turns out after my 18 years of savings, I'm going to expect to wind up with $154,528. So the last thing I'm going to clarify, and then I'll end this video there, is just to mention very, very briefly something about what that last optional argument that I've said a couple times. I'm just going to ignore that. It's called type in Excel. What does that thing represent? So if you look at the cash flow diagram that I drew here, okay, you'll note the last $5,000 deposit that I make, I drew it as happening at the same time as I calculated that future value, okay? And in general, the time value of money functions that are built into Excel and built into your calculator are going to assume that the future value, or FV, is happening at the same time as the last payment, okay? But the first payment doesn't happen until one period after the present value. So another way of saying that is that by default, we're going to assume that each of those payments happen at the end of a period. The first payment happens at the end of the first period, and the last payment happens at the end of the nth period. Now, that may be an entirely realistic way of interpreting the question, but there might be another realistic way. So your son is born today. You want to set aside $5,000 per year for the next 18 years. The calculation that we just did in Excel assumes that our first $5,000 deposit is going to happen not the day he's born, but at the end of his first year, so on his first birthday. And the last of the 18 deposits is going to happen at the end of his 18 years on his 18th birthday, the same day at which I'm going to then wind up with $154,528. If, in contrast, I took that formula and I used that optional argument, okay, and you'll notice Excel gives me a little bit of feedback. 0 means that each of the payments happen at the end of the period, but I could add a 1 to that last argument if I wanted to say that the type of an annuity was an annuity where each of the payments happen at the beginning rather than the end of the period. And you'll note if I use that 1 rather than leaving it out or optionally including a 0 as that last argument, I get a slightly bigger number. And why is it slightly bigger? Because this calculation is now assuming that I make the same 18 deposits or savings on behalf of my son's future tuition or whatever, but that I start making the deposits a year earlier. So it's the same 18 deposits, but the first one happens the day he's born. The last one happens on his 17th birthday, a year before I start making withdrawals. And so what's happened is each of those $5,000 deposits, each of those 18 deposits has had 1 extra year over which to accrue interest. And so the balance at the end of those years is going to be larger. So let me just sum up there. I would note again that we've got access to 5 functions in Excel. Those 5 functions are all available on a financial calculator. They're available in Apple numbers. There is algebra that you could use to solve these problems if you prefer. The names of those functions are the names of the associated concepts. And in general, what you're going to do is use a function whose name is the thing you're trying to figure out. And then you're going to need to plug in the other 4 quantities in order to solve that thing. Talk to you soon.